Okay, good afternoon. I'm Karl Stringer. I am a co-founder of a company called MirrorWeb, and we are a social media and website archiving company. Our primary line of business is to provide social media and website archiving for compliance purposes in the financial sector. We've recently taken over a contract with the National Archives, to provide all website archiving for central government website content and all of the content that's pushed out by the government accounts on Twitter and YouTube, possibly other social media platforms in the future. But for now, we focus on Twitter and YouTube for the National Archives, other platforms for the financial services sector. As I said, we've recently acquired the contract for the National Archives, which it's going to involve an initial ingest of over 100 terabytes of existing data that the National Archives hold from their existing supplier. We need to make sure that we can solve the challenge of serving a front end that's going to be capable of serving 100 million requests per month. So if that was something that we were going to be deploying on traditional hardware with our own load balancers and such like, it would be a bit of a challenge. We'd have all the issues of having to mitigate against unexpected load. So as we'd expect when the service goes out, there's probably going to be quite a strong media focus on it. And when that happens, we need to be confident that we can take on that peak load. It may end up being way more than that expected load. But as you'll understand with serverless, doesn't really matter. The service and the technology can scale automatically from AWS to deal with that for us. This service is due to launch in summer 2017. So by that point, we've got to get everything set up, we've got to get everything provisioned, we've got to deal with the ingest, we've got to deal with all our testing and get everything integrated and ready to go live. And as the government has got a fantastic cloud-first strategy, that enables us to really embrace cloud solutions like AWS. Whereas previously, the issue around data sovereignty and such like might have been a concern, we've now got the London data center. So that opens up a whole new array of options for us now. So originally, when we built the MirrorWeb service, we built it as a monolith, it served our purposes at the time. We put all of our website archiving technology and our social media archiving technology within the same system. That also included things like our reporting engine and user management. It seemed logical at the time because there was a lot of code that was kind of shared functionality between business logic, but as we continued to develop the product and we threw more development resources at it, it became a bit of a nightmare to maintain. So we'd end up in the position where if we wanted to roll out a quick patch or a small fix to, let's say, Twitter changed their API and we need to implement a change, that would mean in the monolithic structure, we'd need to deploy everything again. We need to update all of our servers. So to just change one simple thing in a Twitter API, we'd have to roll out all our web archiving servers again. And everything just became a bit of a nightmare to maintain, really. So at that point, we looked to start moving things out into microservices. So all of our website archiving technology became one microservice. We'd move our social media archiving technology into another. So they were all self-contained chunks of code rather than being in this one big monolith. And initially it was okay because we'd have a developer working on web archiving, another on the social archiving, another doing the reporting stuff. But then as we started to focus more of our attentions into developing the social media product, we'd kind of just be encountering the same problems that we had with the monolith. So trying to track changes and make sure that other people's changes didn't conflict with each other. And then again, if we're in the middle of a big code deploy and something's holding that up, what do we do then? Do we have to wait for that whole development cycle and extend the sprint in order to be able to service it? So really all we found is by splitting our monolith into 4 sections, we just basically created the same problem 4 times, albeit on a slightly smaller scale. So it was at that point, it was actually July of last year when we were at the AWS Summit in London, we made a conscious decision to soak up as much information as we could about serverless. Because we wanted to be able to rapidly deploy and to just change with our changing business. So we got to a few great talks at the summit, and we got some time with Matt Johnson, solutions architect who's here today. And we really helped us to formulate an idea of how we could use this technology to completely change the paradigm from having this kind of boxes of code into completely separating it out into reusable pieces. So it was at that point that we decided to experiment by breaking our social archiving microservice into a series of individual Lambda functions. So rather than having one collection of code that would deal with all of the requests coming in, we'd have one Lambda function that would, its sole purpose would be to connect to the Twitter API and download a list of new tweets from Twitter for a particular account. We'd have a separate Lambda function solely responsible for downloading images. And that could be made in a generic enough way that as long as you know the input parameters and the expected output parameters, you could make that completely reusable. So anything that needs to download an image could use that same block of code. We'd have a separate Lambda function to return content from our database to the user, and another one for all sorts of data aggregation. Only listed 4 there, but we're probably in the hundreds at the moment with all of our Lambda functions. And the beauty of that is each one can be managed independently. If we needed to roll out a change to the Twitter API at this point, actually Twitter changed their API in September. I believe it was the 19th of September last year. They changed the way that the Twitter API worked, so we needed to roll out a quick fix. And all we had to do was update that one Lambda function. We didn't have to worry about all of the issues as regards integration, because we knew that the same input and output parameters were going to be there. It's just that we restructured the Twitter request within that function. So that maintains the interoperability. The problem that you've got when you break things down into this kind of structure, as other people have mentioned, is how you go about unit testing and full flow testing to make sure that your application works. There's a number of ways you can go about it. You can write a completely separate test layer that runs on your application, or it's a bit more of a challenge to actually test on a per function basis because you're building this code into Lambda, into the cloud, but there are ways you can go about it. For instance, when you build your Lambda function, you can also build a command line variant of it, and you can run your tests directly against that then. But that code wouldn't get triggered if it was running within the Lambda environment. The beauty of this as well, using Lambda, is, as everybody else that's spoken has said, you only pay for it when it's running. So there's an example here. We have a single Twitter account that we were archiving, and through the nighttime hours, there was no activity. So we set up a chain of Lambda functions that only trigger in the instance that we've got stuff to work on. So if there's nothing to work on, you're not paying for that. And then when the surge comes during the day, when all the Twitter activity is going on, we can just pay for those units that we're using. And on that basis, you pay for the 100 millisecond increment and a combination of the increments in 100 milliseconds and also a resource allocation in 128 megabytes for your simple level. And you can increase that. I think it's 64 meg chunks that it goes up. And as you increase your memory allocation, it also increases the CPU allocation as well. That's something that I've not seen documented, but it's something that we've heard. And also on the right there, we can see execution duration, and all this information is available within CloudWatch and also within the Lambda interface itself. So with this, you can get really detailed metrics. You can drill down how much it costs to download a single tweet and all of the media that's associated with that. You can work out how much your image download is costing you as a component of that system. So in the ability to drive down costs and improve your efficiencies there is absolutely incredible. It's now becoming the most used component of the AWS infrastructure for us, and we're doing as much as we can to move completely serverless. Just that ability to work out unit costs is fantastic. And if we can compare that against maybe running an EC2 for a month that may be doing all of the Twitter activity for us, that's not going to be utilized all the time. So we can't accurately derive a unit cost on that basis. But by using the serverless technology, by using Lambda, and you get those detailed metrics, it's fantastic for us. So Lambda's only one of many components that we're using on the serverless model. There are more than we've got listed here. For instance, you've got Cognito to deal with your authentication, CloudFront and such like. But the 5 core ones that I want to focus on are these. As I've discussed Lambda enough already, we've got DynamoDB, which is Amazon's NoSQL database system. That's a very highly scalable and highly available system, which rather than you having to provision a cluster of servers of a particular size as you would on a normal relational database system, you just provision read and write capacity on that. So if you know that you're going to need a particular throughput of read and write units, you provision that on the database and then you pay for your access and your use of that and the storage of your data. The objects are stored effectively like JSON files, so you don't have to worry about schema changes or anything like that. And Amazon will deal automatically with all of the sharding and such like. So it is massively scalable. And you can also attach events to it as well. So you can attach, let's say, when a new record's added into a DynamoDB table, that can trigger a Lambda function that can set off a whole chain of events. It's brilliant. We've got API Gateway, which acts as the API layer that it sits in between, let's say, a front-end website and your Lambda functions running in the background. So you can build your own APIs with that, again, scalable, highly available. We've got Amazon S3, which we use as both an object storage system and as a static content delivery system. Absolutely brilliant, again, scalable and highly available. You don't have to worry about provisioning a storage server of a particular size because AWS deal with it all for us. And finally here we've got step functions, which is something that was released on the 1st of December. We were anticipating it and we picked it up as soon as it came out. It's already becoming quite a core part of our service now. I'll explain a bit more later, but step functions basically let you chain together certain functions of activity to form logical flows. So you can build mini applications out of step functions and a handful of Lambda functions. It enables you to do parallel steps, decision steps. So if a particular Lambda function fails, you can handle how that failure logic works. Does it retry? Does it move on to a failure step and such like? It's incredible. Now, all of these, because there's no infrastructure that we have to worry about, means that our requirement on our DevOps and infrastructure management team is kind of shifted. They're no longer now responsible for provisioning servers and making sure that instances are patched and such like. Our infrastructure guys can now focus on writing infrastructure as code. So all of our cloud formation and automatic deployment systems can be managed by the same guys that would usually have been sat there provisioning systems. And because it's all automated, that can respond rapidly to any changes that we make as well. Now, there's a very basic example here. I've stripped out some of the functionality, such as caching layers and authentication layers, because I just want to focus purely on these aspects. But the serverless model means that we can deploy a whole management interface without having to worry about a server. If you've got an interface that's only being used within office hours, then you've probably got 12, 15 hours a day when those servers are not being used. But you still, if you're on a traditional model, you're still paying for those servers, whether it be provisioned tin or physical servers that you've got, or maybe auto-scale groups within Amazon. You're still going to be paying for those resources. Whereas with this model, you're only paying for the requests. So, for instance, Amazon S3, I said we use as both an object storage and as a means of serving static website content. So that means it can't actually do any processing of server-side code, such as Python and such like. However, because it can deliver client-side code, such as JavaScript, we're able to serve let's say a React or an Angular driven site to the end user, which in turn can connect into an API gateway to respond to any interaction with the user's browser. So let's say you need to complete a form on the website, and you click submit. That can post straight to API gateway then. API gateway in turn attaches particular endpoints to Lambda functions, which then can commit to DynamoDB. It could upload into S3 and such like, and then return the response back up to the browser. So whilst S3 is advertised as not being able to support dynamic content, you can build a completely serverless model with it. And the ability there for us not to have to worry about scaling is fantastic. We could deploy this, and we could know that it would serve our clients' needs absolutely perfectly. And similarly, you can apply the same logic to processes that do not involve any human interaction. For instance, we could set up a CloudWatch event, which could act like a scheduled task, to execute a Lambda function with particular parameters that we supply to it. This actually is a simplified means of how we do our Twitter archiving. So for each account, we would set schedules. The Amazon CloudWatch event could actually then, there are limitations on how many actions you can actually set up within it. So the Lambda function there could connect into a DynamoDB or a schedule list within S3 to know what it needs to act upon at a certain time. And then let's say in that first Lambda function we find 100 new tweets that we need to archive. So the Lambda function would format that into the particular JSON style format that Amazon DynamoDB wants, pushes those records into DynamoDB as a batch. We've then got 100 new items sat in DynamoDB ready to be processed. We have another Lambda function attached to inserts on that table. So 100 Lambda functions are then executed at the same time in parallel. And they can be doing all sorts of processing on that data, aggregating the results or working out, deriving if there's any media files within those tweets that need to be downloaded. And from that Lambda function then, we can make a decision whether a step function needs to run. Now, as I said, the step function is a kind of a collection of activity that needs to be executed within a certain logic flow. And we've got an example here. So once we've dropped into the step function, you supply JSON input to it, and that will trigger off a series of Lambda functions or decision steps. So at the top there, we check to see if there's any media files associated with a tweet. So that will then produce, let's say, an aggregation of a number of videos and a list of videos, same with images and such like. And that passes it down into the ringed area there, which is a parallel step. Now, before the process moves on to the next step, that's to the end, but there could be another sequence of events after it. All of those steps need to complete for it to move on. So we go into a parallel step straight away there that downloads images using a reusable piece of code that just accepts an expected input and then gives an expected output. You don't have to do anything with the output, actually. You can just end the process at that point, as we're doing there. And it also drops into a second stage there, which checks to see if there are any videos supplied. Now, rather than that being a Lambda function, that's actually a step function choice. So that will check the data to make sure if it needs to do anything with the actual supplied JSON from the previous function. And then if there's no video, it exits. If there is a video, it will take the right-hand side branch and download the video and save the information to S3. Now, in this case, the tweet that we ingested didn't have any video, so it went to the no video section. And the reason that we've done this is because Lambda isn't suitable for everything. If we need to download a video, so it could be a gigabyte video from YouTube, the time and the cost that would take to run it as a Lambda function with the resources that we need to provision for it isn't a best fit. So that actually goes out to, well, it could in this instance be an EC2 instance, or it could be a Docker instance that connects as an activity task into the step function. So you can actually run permanent servers that connect. In simple terms, it works a bit like a RabbitMQ queuing system type thing. It has a queue ID that it's polling against, and it goes and checks periodically to see if there's anything it needs to do. And the step function, if it was in that step, would just sit there and wait for one of those servers in the activity queue to pick a job up. So you're not just limited to using step functions with Lambda. You can actually use it to execute real-time processing on separate servers, on physical servers or EC2s. Now, the thing that makes the step functions fantastic is that you're not actually paying for the time that these are running. You're actually paying for the transitions between steps. So it does drive up the cost a bit because you're then paying for state change transitions, and you're also paying for the Lambda function code that's running. But the ability for you to chain actions together and build full mini applications with it it's brilliant. And it also means that our non-tech staff, our non-developers, can start building workflows. So if we were to extend this to do, let's say, LinkedIn, all we'd need to do is write another piece of code that ingests a LinkedIn account and passes what this flow expects. Or we create another flow that has different chains of events. So we've got the original step function there on the left-hand side, and on the right, I'm just showing a really basic example of a stripped-down version.
Can you start
At the beginning. So again, on the right-hand side there, we're checking to see if there's any media associated with an item. In this case, that was a very rudimentary example of a YouTube archiver. Now, we know if we're archiving a YouTube channel, there's always going to be a video, and there's always going to be an image associated with it as a snapshot image. So we've got no need to go through this complex choice step. We always know there's going to be a video. So we drop straight into the download video and download image system there. So as you can see, we're recycling the same download images function. We've made it dynamic enough that it can interpret any input. We can supply a specific S3 bucket that data needs to go into. So the previous step there, tweet has media and get media list, will supply parameters to the image downloader that tells it where it needs to store it. So we'll, for specific clients and specific social media channels, we'll be storing them into specific buckets. And that's completely customizable. You write your code to handle that. And you can also set environment variables above that level. So you can have default parameters that will be taken if you don't actually supply it specifics. And the same there, we've got the download video code, which, again, both of those are the same piece of code that run as an activity step, but they're implemented in different ways. Again, because we know the expected input and output, as long as the previous step's catering for that, we can chain them all together. So, as I mentioned earlier, we've got the challenge where we're going to be ingesting over 100 terabytes of data for the National Archives. Now, we've got visibility of the data. We know that it's going to be 1 million files, each of 100 megabytes in size. So we're thinking, can we do this serverless? It's kind of like, traditionally, we would have to spin up a Hadoop cluster and deal with a whole nightmare surrounding the way that that data would be put together and the way that we'd be able to process that. And it's a lot of infrastructure to start managing. So because we know that these files are 100 megabytes each, and we can get Lambda instances that can run at 128 meg, we could theoretically load that into a Lambda function, run 1 million Lambda instances, 1 million Lambda executions to produce 1 million index files. Now, by doing that, we can massively increase the ability for us to do parallel activity on that data without having to worry about a Hadoop cluster or any other kind of infrastructure behind that. Because of the way that Lambda functions work, and we can get error logs within CloudWatch. We can know if there's any data processing errors with each of those records. We can go back and revisit each of those manually and just rectify the problems that we've got, rather than have to go and revisit a whole batch of data to work back through that. So it's something that's something that we're experimenting with at the moment with the technology. We love the idea of trying to use serverless in new ways and try and apply it to instances that we wouldn't have normally been able to viably deal with large amounts of data in a simple manner. And if we go down the serverless model, it then enables us to rapidly expand. It enables us to release quick patches to our code. It enables us, as I mentioned with the Twitter issue, if we had to ingest a vast amount of data in one go, we'd be able to do that with this. And we wouldn't have to worry about the infrastructure. We wouldn't have to worry about how much it was going to cost, because we're only charged per unit of compute. And as I said, that's broken down to 100 millisecond increments, so your costs can be really driven low. In fact, some calculations that we made, if you were able to do a lot of processing on the lowest level of Lambda function, so running for only 100 milliseconds and using the 128 meg of resources, on that basis, we would be able to run 95 million Lambda functions for the same cost as we'd be paying for one T2 medium instance for the month. And that is a vast amount of processing. That means, breaking it down, it's 36.5 Lambda executions per second if you were to use it 24/7. So if you think if you're then only needing to do that during peak hours, let's say only 12 hours of the day, that's double the capacity. You're running at 70 executions per second there for the same price as one T2 medium. So there's massive cost savings to be made, absolutely massive. As I said, there are instances where it isn't viable. For instance, the video downloading, if you're downloading several gigabytes of video, it might not be viable to run it in Lambda. We are actually experimenting with ways we can do that within Lambda, but as I said, there's always other options. You can run the activity steps with EC2 instances or in other ways that we can actually go about working with that. We're also in cases where we can't actually use the serverless technology. For instance, with our web archiving suite, we've got to run some software that might need some quite beefy servers at times. So there might be times where we are archiving a very small website, and we can dedicate maybe a micro or a small T2 instance to that. And there might be other instances where we've got a massive website that needs a lot of network throughput, and we need to archive that in a rapid amount of time. So we need to provision quite a hefty server there. It could be an extra large server that we need for that. So we can't do that within Lambda. But the way that we like to use the technology, we want to make things like EC2 instances as serverless as possible, kind of force them to be a bit serverless. So we can actually run the steps I was talking earlier with setting up a scheduled task to launch an EC2 instance of a given size, so we could work out what size we need, provision that server, launch it from Lambda. That would run for the length it needs to run, do all the archiving it needs to do, upload all the data to S3, and then the EC2 instance can just kill itself. So the EC2 instance there only runs for the time it needs to run. And then we just get rid of it. As you pay by the hour, then we just make sure that we can still derive a cost from that as well. And we're always looking, like I said, we're looking at other ways of using the technology. Any ways that we can go to serverless, that is now becoming the first question that we ask, can we make it serverless? If we can't make it serverless, the next question we ask is, can we make it as close to serverless as possible? And it means that our core infrastructure is now becoming about 80% serverless. And we're looking to drive that even further towards serverless as much as possible.
How do you go about, I guess,
Sorry.
Orchestrating multiple lambdas, or is that different? Is that the wrong way to think about it? Should you never have an idea that anything would be dependent on a few different things?
The idea is that the code is stateless, runs when it needs to run within Lambda. So you would focus, or the way that we do it, we focus on creating a function that does one thing and does it well. So let's say we hooked up an image processor to uploading image files into S3. So for instance, if we downloaded images from a tweet and then we wanted those images formatted in different ways, so creating a thumbnail version, a large version and such like, we would then pass the event from S3 straight into the Lambda function, and Amazon deal with that automatically. So all your code needs to do is work on how to deal with that one image that it's supplied. So the scalability then, it shouldn't have any bearing, because each image that you output or code that's processed will have its own separate output. It's just responsible for doing one specific task. Does that answer the question?
It does. I think I'm more just thinking about, for example, connecting to Twitter and getting accounts on Twitter. Whether they're so separate that one change to one would never mean you need to deploy to the other.
We'd connect to the Twitter API and ingest whatever's new and available at that time. So let's say there were 50 tweets since our last tweet that we retrieved. We'd take all of those and dump them into DynamoDB in one go. And then each of those 50 will be assigned automatically to its own Lambda function. So there's different applications. Some things you are going to be inserting data into tables in bulk, but then Amazon will kind of just deal with all that for it. You can specify what goes to the function when it ingests, so you can actually say that it can deal with, let's say, 10 records, but we just narrow it down, say just send it one to the Lambda function. Is that what you're asking?
It kind of, yeah. I think basically, I think the answer for me is you don't ever have Lambda functions that have any kind of reliance on anything else. So
no, it should have an expected input and output, and as long as that's supplied, you could do that by chaining it in step functions if things had logical flow. But generally speaking, the way that we use Lambda functions, we connect it into the API gateway so that it handles particular endpoints, and it's just responsible for that one task.
So I suppose what I'm thinking of in that particular example is you take an input, you change what the output looks like, but another Lambda function is expecting the old output, and they might need to go out together.
You can tell a Lambda function to just return the same output as it received as input. So if things are reliant on the same data, you can just pass that through anyway. So generally with them being stateless and with them being decoupled, the idea is to try and make them as kind of separate in their own right as possible. If you've got some code that needs to be doing separate steps, then you probably look, should it be one Lambda function that combines different bits of logic, or should it be several Lambda functions, or should you chain it into a step function and build like a mini app for that then?
It's a question I asked downstairs just now. Sorry, apologies for coming in late. Clearly, serverless is an emerging space and sort of good practice around architectural principles, how to design services, how to code well, how to chain things together. These are kind of all emerging. And just out of interest, I mean, how would you recommend, for someone new to serverless, how would you best recommend getting up to speed with what is good practice?
For us, it's been a bit trial by fire. We've been lucky. We've had a lot of interaction with Amazon, especially with solutions architects, especially Matt Johnson. It's a complete paradigm shift. So whoever you speak to, they've all got different ideas on how you should do this. There's a lot of people that stick to the serverless framework type things. You've got serverless, you've got Chalice, which is AWS's implementation. There's Zapper, where you can wrap let's say, a whole Django app into a serverless process. You could run Django serverless, basically. But those frameworks, essentially, you write your code as a microservice or a monolith, and then the technology behind it is just responsible for creating that as serverless. So there's issues there that we found in that your code is still getting kind of limited by this structure in a way. So to get started with it, what I would probably recommend is knock up an API, use an API gateway, attach some Lambda functions to it separately, and just really get a feel for how it all fits together and how it interacts. And you kind of, we found we organically grew into this best practice that really worked well for us. I honestly don't think there's one kind of straight answer of how you should do it with serverless. It's so new, and there's so many kind of polar directions that people take it. But all of them seem to work.
Hi. Just the practical side of things are getting started. I've never written a Lambda. But if you can write a web service, can you write a Lambda?
Definitely. Yeah. You could write an API layer and a Lambda function. You could write a hello world example using API gateway and Lambda in probably 3 minutes. Yeah, it's fantastic. You could do it all through the Amazon interface. So you could set up your endpoints and such like, and just plug it into a function. And the Lambda function, it currently supports Python, Node.js, and C#. So you've got different options. That's another thing I didn't actually mention earlier. It means that we can take on developers that, we're predominantly Python, but we can take on developers that aren't. You can have Lambda functions each in different programming languages. We could have someone developing in Node.js, someone in C#, and us in Python. And as long as the input and output parameters are right, then the code will be interoperable. It's fantastic. I wouldn't recommend just letting people go lose whatever tech they want. It's just theoretical.